Okay, let's start. So today we're going to talk about the free central limit theorem, and if time allows, and I believe it will, we will end with talking a little bit about the non-crossing partitions and counting some subsets of those non-crossing partitions. But we'll start with the free central limit theorem, and I'll remind you what we're dealing with. So we have, as always, we have a non-commutative probability space, and we have a sequence of variables a1, a1, a2, this, 3, so on. The three identically distributed random variables. So I say they are FID, free and identically distributed, and they are all centered. So phi of AR equals 0 for all R, obviously for all R because they are identically distributed. And what we're looking at is the sum of the elements A1 plus A2 plus and so on to AN, and we normalize by square root of n. And the question was, what does this converge to? And we call this convergence by distribution, the definition we've seen in the lecture. And this convergence to an element that we call a semicircular element, which I'll denote here by SA. And for a semicircular element, we need to specify one more thing, which is what? Do you recall from the definition?
The radius.
The radius, right. So we need to specify one thing, and it can either be the radius R or the square standard deviation, which can be calculated to be R squared over 4. But you need to specify either one. And today, for simplicity in the lecture, Gil said, let's assume that the variance is 1, but in general, it converges to this thing, which should equal the phi of, let's say, AI squared. Okay, so the variance of the eventual element is the variance of a single element in the sum. And just for things to make things cleaner later on, I want to specify what does it mean to be a semicircular element. And I will talk about distribution in the algebraic sense. Okay, so for me, in the context of a non-commutative probability space, a distribution is just a sequence of moments. Okay, I don't mind eventually I care about the analytic sense of the distribution, but not in this exercise today. So what does it mean to be a semicircular element? It means that phi of S to the 2k, odd moments are 0, and for even moments, what does this equal? Catalan number times.
So we call it the number of
No, just this, even before today's lecture, what the semicircular element, if the variance was 1, this would have been the answer, but generally it is sigma to the 2k. Okay, Catalan number times sigma to the 2. Now, let me, even though this is the thing we aimed for in the lecture today, this is the simplification we got to, I want to overcomplicate things for now and recall other ways to write this, this same thing. So another way for writing this can be having a sum over all non-crossing pairings of 2k elements of sigma to the 2k. I mean, the term here doesn't depend on the pairing pi, so this is just multiplying by the number of them, which we have seen is the Catalan number. And this can be written even in a weirder way as sum over the same set of the product every P and Q pair in the partition pi of sigma squared. Okay. And an even funnier way to write this is to replace this sigma squared by phi of s squared, but let's say phi of ss. Okay, it is a weird way to write the same thing, but the idea is that the sigma to the 2k appearing here can be expressed as, well, I take combinations of many pairs. Eventually they are the same because I take every time the same element, but I take a pair and I compute the moment of this pair, and this pair is always the same element. Okay, so this is just a weird way to write this distribution, and we called in the lecture, we called this thing kappa of pi. And now I want to ask something slightly different now, and I ask the following question. What if instead of just A1, A2, and A3, and so on, I had here pairs of random variables where each pair is free from the next, but from each other, but I'm not certain that these two are free from each other, but their correlation is the same one as these two. Okay.
Like every joint moment.
Exactly. So the joint moments, let's say the joint moment A1 squared B1 A1 cubed B1 to the 4 is the same as if I would replace the 1 here with any index R. Okay, so their joint moments are the same for each pair, but the pairs are freely independent. Okay. Now, one thing I know for sure is that the marginal distribution of the B's converges as n goes to infinity to some semicircular element SB, which is just the same as here, just the standard deviation might be different, relevant for the B's. But what I ask is, what is the joint distribution of SA and SP? So, yeah. The joint distribution in the algebraic sense of SA and SD. And to answer this question, I need to explain what do I mean by, so I have two sequences here, which I'll denote, let's say, by xn and yn. So I want to say that those sequences as a pair converge to the pair of random variables with some joint distribution. So to even have a discussion here, I need to explain what do I mean by this convergence of more than one random variable. And the definition is just what you would probably expect. So I'll write down the definition for a pair of random variables, but it will be the same concept for any number of them. It can be even an infinite set, but I won't need it here. So we say that a sequence of pairs x and y converges to a pair of random variables x and y if for every joint moment, I'll say it in words and then I'll show an example to clarify, if all joint moments converge or converge to the corresponding moment. Converge to the informally correct moment. So I'll explain what I mean by an example. So if I want to look at, let's say, the moment of xn cubed, yn, xn squared, yn cubed. I want to say that this moment, as n goes to infinity, equals the moment of x cubed, y, x squared, y cubed. Okay, and this should hold for every joint moment. Okay, so this is just an example to clarify what I mean, but writing the formal definition of it is quite clumsy, but I guess it's quite clear what I mean. Okay.
Each joint moment may have a different speed of convergence.
Right. Yeah, this was true also for the standard central limit theorem. We first fix the moment we're looking at, and then we take n to infinity. Indeed. Okay, so to answer this question, I want to ask, okay, what does this converge to? And for doing it, I'll prepare another definition, and then it is going to be clear what will the exercise be, because otherwise I wouldn't define this definition. So, but the idea is that we need additional information about for example, the pairs here. And do you have any guess what this information might be? I'll give a hint. The only thing we cared about for the sequence of A's is that they're centered and their second moment. And we don't care at all about any other moments. This result does not depend on, let's say, phi of A cubed or phi of A to the fourth. We don't care about it. Also in the tensor central limit theorem, right? The condition on the A's is pretty loose.
The smallest one you can think of is like P of ADAB and PIDA.
Or just P of AB.
And that's always
They're not free. Oh, so that's it. If this is an interesting topic as well, and we'll talk about it at the end, but what happens if the A's and the B's are free? But I do not assume that. The pairs are free from each other, but A and B are not, A1 and B1 are not necessarily free. I don't know. So The additional information I expect, in following the proof that we've seen today in the lecture, the thing I expect to maybe intuitively be taken into account here is moments of the form phi of ARBR or phi of BRA. Okay, so this is what I would expect to see in the analysis. Okay, so I will define something that's called the semicircular family. So we say that S1, S2 up to says M. I think I denoted it in the notes. Is it? Sorry. Yes. Okay, is a semicircular family with a covariance matrix C of dimension m times m, if the following holds. We have that for any sequence, I1, I2, up to K will be sort of similar to the K over here, some joint moment that will be represented by this sequence. These are elements in 1 to m. We have that phi of Si1, Si2 up to Sik equals taking the sum over all non-crossing pairings of size k has to be even, of the product of all the PQs in pi of the PQ entries in C. So it is going to be, yes, exactly. So this is going to represent, let's show an example and see that this is exactly what we wanted. But just in this scenario where there are just two variables, I want to imagine the case that we have the matrix, let's call it sigma A squared, sigma B squared on the diagonal. And here we have phi of yeah. So AR, BR for some R, they're all the same, so it doesn't matter. And here it's phi of BRA. And if phi is tracial, then they're the same. This is symmetry. But if it's not tracial, it doesn't have it. Okay, so just for example, let's see how this works. So we'll have for any m that's greater than, I don't know, 4 or 3, greater or equal than 4, we can write down phi of S1, S2. How many non-crossing partitions do we have here? Just one, the one that pairs those two elements. So this is the only partition. So it will be the product of just one element. So PQ in this partition of CPQ, and this is going to equal C12, right? a little bit more interesting, what will be phi of S1, S2. Actually, for the examples I've shown here, we just need the M equals 2. So phi of S1, S2, S2, S1, what is going to be? So I need to look at the product of PQ in the non-crossing pairing. So there are two non-crossing pairings here. I need to consider this one, and I need to consider this one. Right? These are the two non-crossing pairings. So let's do a little shortcut here. So for the first, and I sum over both of those. So the first summand is C12, C21. This is for this pairing, and for the second one, it is C11 squared times C22 squared. C without the square. All right, and in a similar manner, phi of S1, S2, S1, S2, I need to treat the same two partitions, but this time I'll get different summands. So for the first one, I'll have C12 squared, right? Because it's the same one for both. The order is important here. And for the second one, I'll get C12 times C21. Okay, so this is not quite the same thing. All right. So this is the definition. And now I want to say that if I want to state the multivariate spectral central limit theorem, and it is stated as follows. So let me adjust a little bit what's written here. So I have sequence of sets of elements, not necessarily two, where I is in some set M. And there may be more than two. And I want to say that they converge to, I have xn I, or one particular index here, they converge to an element Si, such that the Si's are a semicircular family with the matrix Cij defined by phi of for any r, they're all this, for any r, the distribution here is the same, but the location in the matrix is just the joint moment of ing. Recall, if I take different r's, these are free from one another, but these, as this is the same r, they're not guaranteed to be free. Okay, so this is the theorem I want to prove, and it will be rather similar to what we've seen in the lecture today, just with a tiny complication that I will get to a term that looks similar to this, just I won't be able to collapse it to this nice expression because the moments, the kappas do depend on some indices, the indices of the upper I here, okay? So let's see how it looks like. from this point on, once I define this definition, the proof is quite straightforward. So in order, we said that we need to look at joint moments, and we look at joint moments of the xi's. So let's understand what this means. So a joint moment of xi's looks like this. So let's ignore the square root of n in the denominator. We'll add it later on. So we have sums of the form a1 plus a2 plus an. I cannot put the power as we did in the lecture today because this is now a joint moment. So I can't tell in advance what it's going to be. So I have a few of those. And the last one, also a1 plus a2 plus up to an. And for each one, I have some index I here. So this is I1 for all of them. This can be any number between 1 and m, this one. And here I have the notation with k. Okay, so I have k terms here. Some of them may be the same, and I care about the I with another index. The ij's are numbers in between 1 and n. Okay, this is a sequence of numbers. And what I ask is, what's phi of this thing? Now again, this translates to sum over, now for each summand, I need to pick the sequence of i's remains the same as it is here, but for every summand, I need to pick one element from this. So I write it down as, so I still go from 1 to k. I have R1 up to Rk that are between 1 and capital N. And I take phi of, and this is going to be variable, R1 R. Okay. And the order in which they come, I need to make it not look like a power. So here I have I1, and here I have IK. Okay, this is the same sum we looked at in class today. And now let's see the few arguments that we had in the lecture today about what terms do we care about. So as we noted, the values of the R's do not matter, just their, Gil did not use this term today in the lecture, but we care about their kernel. Okay, so I say that, let's say the kernel of the sequence 15535 1 is the partition that looks like this. Okay, or you can write it as 1, 6, and 2, 3, 5, and 4. Okay, this is we translate the sequence, and I don't care about the numbers, I just care about how they're connected to each other, which are the same and which are different. So this is the result. And so we don't care about the values, we just care how many of them appear and and which are the same and which are different. And the thing is that we still cannot have a singleton R, no matter what the values of the i's are, since the sets are different from each other. So if I have a singleton here, then this term will vanish. Okay, so we have no singletons. That's one. Another thing is that, and the same argument that we used today in the lecture for crossing will still hold. So no crossing kernels, crossing partitions, because they'll vanish. So we are left with the same argument for okay. So let's say singletons cause okay. The values are going to, the value of the term with a singleton or with the crossing partition is going to vanish. And also, how many moments appear with kernel pi? We've seen that, let's say this is the kernel, so I need to decide what are the values that I'm placing in the given partition, and the number of choices I have here for this particular example is 3. Right, I need to choose one for each part in the partition. And when n goes to infinity, this roughly goes as n to the size of pi. Size meaning the number of parts. Now, given that there are no singletons, then pi has to be at most n/2. So again, I'm left just with pairings, and I need non-crossing pairings. Okay, so let's break this down. What we get is a sum over all I, which are non-crossing pairings of k elements. Again, if k would be odd, then this would be 0, of product. And now for the same argument as before, I will have the same argument as we had in the lecture. Whenever there is a non-crossing pairing, there will be 2 consecutive elements that can be pulled outside of the term for the same reasoning, because we'll always have, let's say, phi of some prefix, call it b, some prefix times a r for the same r, which are consecutive, which might have different indices, let's say ij and ij plus 1. This may be the same and may be different, but this is the same, and in the partition I treat only the lower indices, and some c, and we know that this equals phi of ar ij ar ij plus 1 times phi of bc. Okay, this is the rule we know from Frenes. Okay, so doing this over and over again yields us that I take the parts in pi and take exactly these terms. And phi of a second used here. I want to. Okay, so this is for some r. And I want to take IP and IQ. Making a mistake here. And this should give me exactly what I wanted for the semicircular family. Okay, because I look at, I get something that's not as clean as just counting them, because all the second moments or moments with two elements are the same, but rather I get something more complicated, and I should expect something more complicated because I wasn't guaranteed anything about the joint distribution within each set. Okay, so this is basically it.
Okay, so so let's say side it said they are not free, but they are exactly the same. Example,
They're equal.
yeah,
like,
they are equal. So how can we see it here? Like very simple example. Where they are equal, where the inverses of each other.
Think about it. I was thinking just about the complete, the exact opposite example, which is the case that they are free each other. In which case, since they are centered, this would vanish as well. And what I'll get is that the limit ones are also free. And this is a fact that's not very hard to prove even more generally. I'll put it in the homework, but you're asking about the opposite. Let's say they're the same element. So I guess this would give me, if they're all the same, then I'll get, yeah, this is simple. This is collapses to this case, because I'll have each one of these terms, no matter what P and Q are, this will be not P and Q, I of P and I of Q. Doesn't matter what they are, I'll always have phi of A squared, AR squared, and then it will be just the sum of the same of the same term each time. Okay.
And if let's say you have a minus, so the minus just goes out from everything. And
So you're saying two, let's say m equals 2, so I have two elements, and
have A1 and
so
minus A1.
let's think about what we expect to happen. I expect to have SA to be minus XB in the limit. And so I believe this should work out. I don't quite see it immediately, but I believe it should.
Oh, you just have an even number minuses, and because you have. Oh. Okay.
And we have 10 more minutes, so it's enough time to do something slightly different and just talk about non-crossing partitions. And what I want to do is count one very specific thing, and I'll do a favorite proof by picture. So let's see how it works. So the next exercise is counting let's say how many non-crossing, say, pi in non-crossing partitions, not pairings, of size call it n because we have no capital N, with size k. Okay, so I'm looking at non-crossing partitions of n elements, but the partitions are for, let's say, 3 parts or 4 parts. I fix k is fixed, and ask how many such partitions exist. Okay. And maybe you can count it directly. I wasn't able to, because I was following some particular exercise that did what I'm going to do. But the idea is to do some manipulation to this question in order to get to something that I'm able to cover. So I'll start with an example. Let's say n equals 6. And I have the partition, let's write down 1, 2, 3, 4, 5, 6. And the following partition. 1 is connected to 3 and 4. 2 is on its own, and 5 is connected to 6. And for this partition, I want to draw something. So let's call this one 5. 5 is actually 6 partition, no partition. And I want to draw pi as the following correlated path to it. So I start at 0, and what I do is I say, okay, what is the size of the non-crossing part that of the part that one starts? And this is of size 3, so I'm saying it's 1 plus 2 elements. So I take 2 steps up. Okay. And now I ask the same question about 2. So how many more elements are added to 2? 0. So this goes straight. And then 3 and 4 do not open a new one. So I take steps down in the grid. Okay. And then I do the same thing for 5. And same for 6. And this is the path that represents this partition. Now, what I want to say, without even defining anything on this side, which I'll define in a moment, I want to say that the process I just described is a bijection. Bijection to something, to some object that I didn't name yet. How is this a bijection? Because, first of all, let's try to understand what we see here. We see a path, and all the steps are to the right, and they're allowed to be either any number of steps up, including 0, and it can be 1 step down, and they never go below the axis. Okay, so I'll name these paths. They're called the Lukashevich paths. And I say that there is a bijection between non-crossing partitions and Lukashevich paths of the same length. And the bijection from, if I want to invert it, I say that I'm doing a projection to the left. So if I draw these lines, I'll show another example in a minute. If I draw these lines, I can understand that, let's say, 1 is connected to whichever steps were projected to it. Okay, I'm not writing any proofs here, but I can recover this partition from this specific Lukashevich.
Can you repeat how you?
Yes, so I see a step up, so I know that 1 is opening a part, and for every down step, I take I look at, this is the step, this is the up step correlated with 1, and every down step that projects to it pictorially. I mean, it's not a formal definition, but it's easier to understand from the picture than any formal definition that I've seen. So the relevant step will be in the same set as 1.
If you take the point like 3, 1, and you take it to the left until you hit
An up step, yes. So this is a bijection. So I need to define something. So we know the set of, we have the set of non-crossing partitions of n elements. I won't be able to make this on time. But what's the preference? That I do it next time, or that will stay 5 more minutes? Feel free to say the truth. Okay. So there is a bijection between between the non-crossing partitions of size n and something. So I need to define this something. So first I'll define an almost rising path for AR of size n. Almost rising path is a path that has steps to the right. So each step is 1 to the right, and let's say A up or down, and A is a natural number, including 0 or -1. Okay, so this is an almost rising path, and the Lukashevich path, I hope I'm writing it correctly, it's correct in the notes. Lukashevich of size n is a almost rising of size n, which never goes below the x-axis. Let's say always above the axis. Always above the x-axis. And at least from the picture, I hope I convinced you that there's a bijection between the non-crossing partitions of size n.
You also need to say that you did it on the
And right. Which is above the x-axis and completed at 0. Thank you. And at 0. That's important. That's crucial. And I can add one more condition here and say that non-crossing partitions of n elements of size k are translated using the same bijection to which subset of the Lukashevich paths?
So the one that goes to 0 3 times? No.
No. There's a correspondence between opening parts and steps which are not going down. Right? So here, these are Lukashevich paths with k steps which are non-negative. K non-negative steps. Okay, and this is the same bijection, just a subset of the partitions here and subset of the paths. So I translated one problem to another, but this is still difficult to count. Similar to the Catalan problem when you need to get to a certain point and not go below the line, right? So it's still not very clear how to count it. So I want to do a slightly, I want to do a tweak on this idea and say that instead of taking a Lukashevich path, I take the Lukashevich path and permute it. And let's say I permute somewhere between here between 1 and 6. So let's imagine I start my walk at number 2. So how would this walk look like? Let's start it from here.
Down, down, up,
Down, down, then
down,
up, down, then
up twice.
twice, and right. Okay, and So these are, because the original one ended where it started, then this tells me that wherever I start, I'll end in the same place that I started. And what I want to have is try to look at paths that, trying to understand, like from the permutation, try to understand what was, without giving, I want to remove the restriction of going below or above an axis to make the counting problem easier. And this doesn't quite cut it. I mean, this doesn't quite help me. So I'll do one more thing, and I'll add an additional step down at the end to get to minus. I'll show you in a minute why am I doing it. And now if I do the same thing, let's try it again. So I do, I have down, down, and then up, and then twice I'm going down, and then I'm going the long step up, and staying the same. So if I imagine this was 0, so this will end in a -1. And what I claim is then that once I add this additional step of -1, the first location in which I hit the bottom point, there may be, in this specific example, there's only one, is in direct correspondence to how did I permute the original path. I think I won't make this in time, so let's cut it here and either continue next time or I'll publish something to be clear online. So I will complete it later.